Hello viewers, welcome to the channel Amazing Civil Engineering Studies. Time to enter the world of civil engineering. Here we will learn about different concepts related to civil engineering. Please subscribe to the channel and press the bell icon for more new updates. In today's video we are going to discuss about geotechnical engineering, soil, stresses in the ground. Stress in the ground. There are 4 types of stresses in ground. These are discussed below. Total stress, pore pressure, effective stress. Calculating vertical stress in the ground. When a load is applied to soil, it is carried by the water in the pores as well as the solid grains. The increase in pressure within the pore water causes drainage, flow out of the soil, and the load is transferred to the solid grains. The rate of drainage depends on the permeability of the soil. The strength and compressibility of the soil depend on the stresses within the solid granular fabric. These are called effective stresses. Total stress. When a load is applied to soil, it is carried by the solid grains and the water in the pores. The total vertical stress acting at a point below the ground surface is due to the weight of everything that lies above, including soil, water, and surface loading. Total stress thus increases with depth and with unit weight. Vertical total stress at depth Z, S. V equals G times Z. Below a water body, the total stress is the sum of the weight of the soil up to the surface and the weight of water above this. S. V equals G times Z plus G. W times Z. W. The total stress may also be denoted by S, Z or just S. It varies with changes in water level and with excavation. Pore water pressure. The pressure of water in the pores of the soil is called pore water pressure, U. The magnitude of pore water pressure depends on the depth below the water table, the conditions of seepage flow. Under hydrostatic conditions, no water flow takes place, and the pore pressure at a given point is given by U equals W times H, where H equals depth below water table or overlying water surface. It is convenient to think of pore water pressure as the pressure exerted by a column of water in an imaginary standpipe inserted at the given point. The natural level of groundwater is called the water table or the phreatic surface. Under conditions of no seepage flow, the water table is horizontal. The magnitude of the pore water pressure at the water table is 0. Below the water table, pore water pressures are positive. The principle of effective stress was enunciated by Karl Terzaghi in the year 1936. This principle is valid only for saturated soils, and consists of two parts. At any point in a soil mass, the effective stress, represented by S, is related to total stress, S, and pore water pressure, U, as S equals SU. Both the total stress and pore water pressure can be measured at any point. All measurable effects of a change of stress, such as compression and a change of shearing resistance, are exclusively due to changes in effective stress. In a saturate soil system, as the voids are completely filled with water, the pore water pressure acts equally in all directions. The effective stress is not the exact contact stress between particles but the distribution of load carried by the soil particles over the area considered. It cannot be measured and can only be computed. If the total stress is increased due to additional load applied to the soil, the pore water pressure initially increases to counteract the additional stress. This increase in pressure within the pores might cause water to drain out of the soil mass, and the load is transferred to the solid grains. This will lead to the increase of effective stress. Above the water table, when the soil is saturated, pore pressure will be negative, less than atmospheric. The height above the water table to which the soil is saturated is called the capillary rise, and this depends on the grain size and the size of pores. In coarse soils, the capillary rise is very small. Between the top of the saturated zone and the ground surface, the soil is partially saturated, with a consequent reduction in unit weight. The pore pressure in a partially saturated soil consists of two components. Pore water pressure equals U W. Pore air pressure equals U A. Water is incompressible, whereas air is compressible. The combined effect is a complex relationship involving partial pressures and the degree of saturation of the soil. Effective stress under hydrodynamic conditions. There is a change in pore water pressure in conditions of seepage flow within the ground. Consider seepage occurring between 2 points P and Q. The potential driving the water flow is the hydraulic gradient between the 2 points, which is equal to the head drop per unit length. In steady-state seepage, the gradient remains constant. Hydraulic gradient from PDOQ, I equals H/S. As water percolates through soil, it exerts a drag on soil particles it comes in contact with. Depending on the flow direction, either downward or upward, the drag either increases or decreases interparticle contact forces. A downward flow increases effective stress. In contrast, an upward flow opposes the force of gravity and can even cause to counteract completely the contact forces. In such a situation, effective stress is reduced to zero and the soil behaves like a very viscous liquid. Such a state is known as quicksand condition. In nature, this condition is usually observed in coarse silt or fine sand subject to artesian conditions. At the bottom of the soil column, S equals times L, U equals W. L plus H. During quicksand condition, the effective stress is reduced to zero. Times L equals W. L plus H, L times W equals W times HL times H equals W times H. H/L equals H W equals I CR, where ICR equals critical hydraulic gradient. This shows that when water flows upward under a hydraulic gradient of about 1, it completely neutralizes the force on account of the weight of particles, and thus leaves the particles suspended in water. Importance of effective stress. At any point within the soil mass, the magnitudes of both total stress and pore water pressure are dependent on the groundwater position. With a shift in the water table due to seasonal fluctuations, there is a resulting change in the distribution in pore water pressure with depth. Changes in water level below ground result in changes in effective stresses below the water table. A rise increases the pore water pressure at all elevations, thus causing a decrease in effective stress. In contrast, a fall in the water table produces an increase in the effective stress. Changes in water level above ground do not cause changes in effective stresses in the ground below. A rise above ground surface increases both the total stress and the pore water pressure by the same amount, and consequently effective stress is not altered. In some analyses it is better to work with the changes of quantity, rather than in absolute quantities. The effective stress expression then becomes S equals SU. If both total stress and pore water pressure change by the same amount, the effective stress remains constant. Total and effective stresses must be distinguishable in all calculations. Ground movements and instabilities can be caused by changes in total stress, such as caused by loading by foundations and unloading due to excavations. They can also be caused by changes in pore water pressures, such as failure of slopes after rainfall. Thank you for watching. For now, please subscribe, like, share and do not forget to press bell icon.